This is screencast 4 for week 5 uh, for the course Business Administration 571. I was talking about a way to determine if signal from an X chart is due to a sigma shift or not. And I was proposing that what you do is a sequence of tests of equality of variances between two groups. The idea is that if the second group's variance is statistically significantly different than group 1's standard variance, then the sigma has shifted. The problem is you have to test every partition of the data starting with stage 1 and seeing if the second group in stage 2, the variance in that second group is bigger than the variance in the first group, stage 1, where you knew everything was okay. So I went over the arithmetic involved in computing the test statistic, but since it's sequential, you would either need to write a macro yourself or find one that somebody else has written. Lucky for you, I've got one. So as soon as I can get this to wake up. So we pop into the G drive and look around, and here's a program called Variance Shift. This might be just what we're looking for. So it says, performs a sequence of tests for the equality of variances to locate the subgroup at which the variance shifted on an X chart. Okay, so of course the flip side is if this program never produces a significant test statistic, then the conclusion is that the signal coming off the X chart was due to a mean shift. So what is going to go on here? Well, I just made up some data, 4, 9, 3, 7, 2, 10, 9, 1, 14, 5. Notice that from here down to here, from 4 down to 2, the variance isn't very big, but then we start getting these wild swings. That's a sure sign of increased variance. So I say that this macro is hard-coded for stage 1 size, K is 4, and signal being received on the 6th stage 2 observation. So N naught is 6. So you would need to modify these two values for your application. So the deal is, to implement my idea in SAS, I needed to write a macro. Well, SAS has a kind of a meta language that allows you to treat SAS as if it's a collection of commands inside a programming language. Excuse. So this macro system is invoked by you saying %sign macro, and then the name that you want to give the macro. So global statement macro. Then if you want to perform a do loop, you say %sign do. So anything that has a % in front of it has something to do with the macro language. So let's do a do loop, I running 4 to 8. Okay, so I'm going to be, this is not the I that I talked about in the test. It is an absolute value of I on the absolute index of the data point. So I've got this data set, chart data. I'm going to bring it in. This underscore and underscore is a SAS reserved variable which just basically counts where SAS is as it reads a data set. So underscore and underscore goes through the values 1, 2, 3, 4 as the records are read. If you want to refer to I, you put an @ sign in front of the I to tell it to use whatever value I is on. Now this loop is going to run from this do loop down to this %n down here. So first we're going to build we're going to build a data set that looks just like XChart data, except it's going to have a new variable in it called GRP for group. And we're going to set this group to 1 or 2 depending on whether the record counter is less than or equal to whatever value of I we're on. Now since stage 1 has 4 observations in it, the first pass through the loop, we will put all stage 1 values in group 1 and all stage 2 values in group 2. So what do? Well, we are going to do a t-test on the data set that we just created that has no name, but it's the most recent one, so that's the one that proc t-test is going to use. So t-test is a procedure, as it says here, that does t-tests. It also does the f-test for the equality of variances. I happen to know that because I read about the capabilities of t-test in the SAS documentation. So class group telling this procedure that the group variable up here is a classification variable. I'm going to produce a listing, and then I'm going to print that listing. And I'm going to create a new data set called PRNT for printing, and I will print the results of the test by this proc print right here. MEND says end my macro, but without the M, the END says end my do loop. So I'm going to end my do loop, and then I'm going to end the macro itself. Now, when I teach SAS to more advanced students in the graduate programs, a common thing that they don't do is they go ahead and build the macro okay, but they never run the macro. They think by building the macro it'll also run. Not true. SAS won't do anything unless you actually tell it to do it. So what you got to do is say $var test, which is the name I gave it here. So if you want to call this Linda, and then say $Linda, this will run. So this name is just arbitrary. So let's try our hand at running this guy. So it's running, and hopefully here in a little bit we'll get some output. Now this again is going down to North Carolina, Research Triangle Park, where SAS is located, and that's the majority of all this time that's going by. Okay, so let's get rid of the fluff and see what we got here. T-test. I'm just getting a whole bunch of output, but let's take note of what we have here. The variable x folded f-test. Numerator degrees of freedom is 5, denominator degrees of freedom is 3. The f value came out to 3.35, and the probability, or the p-value, is 0.3492, which is much bigger than 0.05 divided by, well, I guess in this case it would be 2. And this is for subgroup 4. So here's the full t-test output, which I didn't really want. Now we go to subgroup 5. So we've done another f-test. And SAS calls it the folded f-test. So if you want to look into the SAS documentation, you want to search for folded f, not just f-test. Subgroup 5, big giant p-value. Here comes another t-test. Subgroup 6, giant p-value. 2 to go. This guy. Subgroup 7, smaller p-value. How come? Because we're getting closer to where I made sure the variance was getting bigger. So let's look at this last one. Subgroup 8, not so much. So if we were using an alpha bigger than 0.05, say 0.15, we would declare a sigma shift at the point where I is set to 7. And that's about where I started to make the data look like the variance had changed. Okay, so this program, of course, could easily be made more general and modified and put to work in a real setting. All right, well, back to the salt mines here. We have another topic that we need to be concerned about at this point, and that is attribute control charts. Okay, so attribute data. Well, this is the simplest form of data. So what you do is in a batch, or equivalently, a subgroup of size n, count the number of non-conforming units. Call this count x sub I running 1, 2, on out. A plot of x versus I with control limits is called an NP chart, or attributes chart. Control chart. So if there's some rule that a unit needs to adhere to in order to be called a conforming unit, then that's a good unit. But if that rule is violated, then that unit is non-conforming. Let P equal the probability that a non-conforming unit is built. thinking, well, this is only for manufacturing. I'm not going to go into manufacturing, so I could care less about it. Well, let's get creative and come up with an example from accounting. You are working for a small company. A small firm has 1,500 employees. I worked for a firm once that had about that many employees, and in order to stay in the category of a high technology company, you had to have a certain amount of profit. So the president of the company comes around to engineering one day and says, I want everybody who has acquired vacation time to take it this month. We were this small a company. Why, Kleist? Robert Kleist was our president. He says, because I want to get that money off the books, because we're just a little bit below the profit that we need to stay qualified as a high technology company. So I think this will push us right over where we need to be. So I want all you folks who have some vacation time accumulated to take it now. Well, we were a pretty small outfit, so we took that seriously, and people took, their 4 days they'd accumulated, and there went their trip to Cancun because they just stayed home. So you got this small firm. You got an accounting department, and P equals the probability of a paycheck with at least one audit exception. Now, if you were attentive in your auditing course or anything that you took in accounting that had to do with auditing, you heard that phrase. So you got a bunch of people that are working, that are doing shift work in a machine shop, and they've been asked to work overtime, which they do. Their paycheck shows up in their hand, and their wife works out the values, and she says, we got shortchanged yet again. You had 10 hours of overtime coming to you, and they only paid you for 5. And see, look, you got all the times when you punched in and punched out. So you go over to HR, and they say, oh, yeah, sorry, we blew it. Well, this happens all the time in the real world. And those are euphemistically called audit exceptions. They're mistakes on a person's paycheck. So you want to know what the mistake rate is of your hard hitters in your payroll. So you record 4 pay periods and discover 120 paychecks with audit exceptions. So what's P? P hat? Well, it's X over N. But in this case, it's 120 over 4 times 1,500. Why? Because you have a firm of 1,500 people. You're cutting each person a paycheck every pay period, and you watched for 4 pay periods. By the way, this is how every quality improvement program gets started, and that is you watch the system, stage 1, to discover what its present performance is. In this case, you discover that there is a 2% chance that payroll will create a paycheck that has at least 1 mistake in it. So an NP chart is X by I, which is pay period. So what is our batch or our subgroup? It is 1,500 employees. So you want to draw this chart, but what we're missing at the moment are control limits. But let's say, just for purposes of putting some data down, we have 1, 2, 3, 4, and we find we have 19, 30, 41, and 60 audit exceptions. I mean paychecks with at least one audit exception per pay period. So in pay period 1 we've seen 19 checks that have mistakes. In pay period 2, 30 had mistakes, one or more mistakes. Pay period 3, 41, and then in the 4th pay period we had 60 checks out of the 1,500. And so the question is, of course, well, up here is 50, and we've got 1, 2, 3, 4, and we have something that looks kind of like this. So, you know, a non-quality tool student would tell you that you have a problem in the fact that it's pretty obvious to most folks that the rate of mistakes is going up. And it isn't going up all of a sudden, it's going up nice and smooth. But the problem at the moment is, when do you say to senior management, there's something going on in payroll? You need control limits before you can say that you've gotten a signal. Where are you going to get these control limits? Well, it turns out that for this application, the control limits are 47 and 15. Where did you get those? Well, find LCL and UCL for which the probability of X being below LCL is about 0.001365, and the probability that X is bigger than the upper control limit is about 0.001365. Why would I want to use a funny number 0.00136? Because these two numbers added up equals 0.0027, which is X bar's false positive rate using plus minus 3 sigma. Why would we want to do that? Why would we want to arrange the LCL and the UCL to give us a false positive rate of 0.0027? Because we have very patiently taught senior management that these control charts, if they squeal, they should be listened to. Why? Because the false positive rate on these control charts is teeny tiny, 0.0027. And so we want to use this training, this trust that we've built up with senior management, to introduce to them a chart for a service operation, which is payroll. One of the VPs of the company comes from the accounting department, and that person is personal friends with several folks in payroll. You have reason to believe that payroll is suffering a loss of quality. Payroll doesn't make anything, unless you want to call a paycheck something that they make. So this is clearly a service operation, and it has nothing to do with a manufacturing setting. And it has everything to do with people. And whoa, you can't put metrics on people, because people are, like Captain Kirk says, they're just very hard to predict, and they're very creative and stuff. Yeah, but if we're just trying to get them to cut paychecks, and if they can't do that, then we don't care what their other skills are. We don't want them working for us. So it's not hard to put metrics on people. Attribute metrics are the easiest metrics to impose on a service operation. You just simply count how many times things are considered wrong and divide that number by the size of the number of times you tried to do something. And in this case, it is the number of times you tried to make a paycheck without messing it up. So we need to find the lower and the upper control limit so that when P has not shifted, see, what we're thinking here is somewhere in here, N times P has changed value from the original value. Why N times P? Because the expected value of X equals N times P for X distributed as binomial NP. And that binomial is something that I asked you to learn about or review from your 210 book, and it is mentioned at length in Ryan's chapter 3. End of screencast.